Alrighty, hello everybody. In this video, we are going to discuss we're going to discuss chemical equilibrium, right? It's one of two parts, all right? So what do we mean when we discuss a chemical reaction and say that a given reaction is at equilibrium? We typically do use those double-sided arrows to indicate that a given reaction is at equilibrium, right? And what it's telling us is that the change of concentration of the reactants or the product over time is basically very small, right? Or approaching zero. It does not mean that the concentration of the reactants are identical or the same as the concentration of the products. It simply means that the change in concentration over time, the change in concentration over time is basically zero. There isn't really, the concentration is not changing over time. Okay. So then the reaction is reversible, right? We could think of the reaction going in the forward direction where reactants are being turned over into product, or we could think of the reaction in the reverse direction where the products are being turned over back into reactants. Anytime we're indicating that something is at equilibrium, we end up using those a half-headed arrow, okay? Or fish hook arrow. So in the forward direction and in the reverse direction. So when the rate of the forward and the reverse direction is basically equal, then we say that the reaction is at equilibrium, or what we refer to as dynamic equilibrium. And if you recall, when we discussed if you have a volatile liquid in a sealed container, that volatile liquid is going to evaporate into its gas form, and the gas form is going to condense back into the liquid. And at some point, it's going to reach dynamic equilibrium when the rate of condensation is equal to the rate of evaporation. So here we're looking at chemical reactions, reactants being turned over into product, and at some point it reaches what we call equilibrium, all right? So what happens once the reaction is at equilibrium? Does it change? Yeah, we'll see that the reaction will actually shift. It's going to shift to either form more products, or it's going to shift back in the reverse direction, right? And it just has to do with different factors that are altering that particular equilibrium. So we will learn as we increase the concentration of the reactant, if that particular reaction is at equilibrium, the reaction will tend to shift towards forming a more product. It will shift to re-establish equilibrium. It will shift in the direction away from the added change. Right. And if we increase the concentration of the product, then equilibrium will tend to shift towards the left or towards the reactant side again, so that the rate of change over time ends up being close to zero, so that it can re-establish what we call the equilibrium, right? So it's going to shift in one direction or the other. So can we determine the concentrations of reactants and products at equilibrium? We're going to take a look at that, right? So let's consider, before we do that, let's consider a chemical equilibrium again. If we have hydrogen gas and iodine gas reacting to form 2 moles of hydrogen iodide, initially, at the start of the reaction, at 0 seconds, all we have is the reactant. Right? So the concentration of the product is 0. That's initially. So we would expect that the reaction is only going to proceed in the forward direction. Okay. However, as time passes by, the reactants will now begin to be converted into products. And initially, the rate of the reaction is also going to favor the formation of the product. Okay. But both reactions are taking place. And as the concentration of the product increases over time, what's going to happen at some point is that the forward direction will slow down and the reverse direction will begin to accelerate until the reaction reaches equilibrium, when that rate of change of concentration over time is basically, there's no change in the rate, and we had defined rate as changes in concentration over time. All right. So if you take a look at it, initially here at time 0, all we have is the reactant, right? And hydrogen gas is shown as the white, right here, the diatomic molecule. So over time, when time kind of passes by from 0 to like 20 seconds, the reactants will begin to be converted into product. At 35 seconds, reactants are being converted into products, but over time it's going to reach equilibrium. So the reactants are being turned over into product, the product is being turned over into reactant, and otherwise both the forward and the reverse reactions are taking place, right? And that's at equilibrium. Both the forward and the reverse reactions are actually taking place, right? And that's what we refer to as dynamic equilibrium. Okay, so the rate, again, it's the change in concentration over time. The rate of the forward and the reverse reaction is equal, right? So let's take a look at a plot. What do we mean by that? So if we're plotting concentration on the y-axis versus time, on the x-axis, what do we have initially? Initially, all we have is reactants. So the concentration of each of the reactants is high, however much we're using. And the concentration of the product initially was 0, right? We don't have any product initially. And as the reaction begins to take place, as you mix the two reactants, the concentration of the reactant will begin to decrease. Why? Because they're reacting and forming the product. So the concentration of the product will begin to increase. And at some point in the reaction, it will reach what we call dynamic equilibrium. And that's when there is no longer change in the concentration of the product over time. Notice this is concentration and this is time. So that change in concentration over time is basically constant. The concentration is not changing over time. Does it mean that the concentration of the reactants and the products are identical? No. Notice that's the concentration of the product at equilibrium. That's the concentration of one of the reactants at equilibrium. And that's basically the concentration of the other reactant at equilibrium. So the concentration is not the same. The change in the concentration over time, or the rate, is constant. And that's what we refer to as dynamic equilibrium. Can we disturb dynamic equilibrium? We can. What happens if we remove some of the product? Then it's going to shift to form more product. So we're going to look at factors, specifically really changing the concentration and how that will alter that particular dynamic equilibrium. Okay, so let's take a look at it once again. We're plotting again concentration versus time. So initially, all we have is the reactants. Right? We're looking at dinitrogen tetroxide forming 2 moles of nitrogen dioxide. So initially we have, however much concentration of reactant, and the concentration of the product initially is 0. All we have is the reactant. And over time, the concentration of the reactant is going to decrease and the concentration of the product is going to increase. And at some point, the reaction is going to reach equilibrium. And that's when the change of concentration over time is basically constant. And that's because both the forward and the reverse direction of the reaction are taking place at the same time. So you have the forward and the reverse direction taking place in dynamic equilibrium or the reaction is at dynamic equilibrium, right? The rate of the forward direction is equivalent to the rate of the reverse direction. So there is no longer a change in the concentration. All right, well, can we determine the concentrations of reactants and products at dynamic equilibrium? We can, and we can correlate it to what we refer to as the equilibrium constant. And C is really for concentration. And if you take a look at the reaction, if we have A reacting with B to form C and D, okay, the lowercase letters are really the coefficients, thinking we have A moles of A, B moles of B, C moles of C, and D moles of D. Well, when we write out that equilibrium constant, it is equal to the concentration of the product, each raised to its coefficient, divided by the concentration of the reactant, each raised to its coefficient, right? Again, the coefficient is really the number of moles, right? So each is raised to the number of moles. Okay, so product over reactant, right? Well, let's take a look at it. The reactant is in the denominator and the product is in the numerator, right? If we increase the concentration of the product, we would expect the equilibrium constant to be higher, right? If the concentration of the reactants are larger, we would expect that the equilibrium constant would be smaller. Well, this equilibrium constant tells us if the reaction is right at equilibrium, or if it slightly favors the product, or if it slightly favors the reactant, right? Sometimes we'll use the arrows that will indicate the one that is slightly favored by having a larger, basically, arrow. Okay, so the equilibrium tells us that. Does the reaction favor the product? Do we have more product at equilibrium, or does the reaction favor the reactant at equilibrium? Do we have more reactants at equilibrium? All right, so we're gonna consider dinitrogen pentoxide, or 2 moles of dinitrogen pentoxide forming 4 moles of nitrogen dioxide and 1 mole of oxygen gas. How would we write the equilibrium constant, right? Again, the equilibrium constant is the concentration of the product, each raised to its coefficient, right? And this is basically 1. So that's the 1 over the concentration of the reactant, each raised to its coefficient as well. That's the equilibrium constant in terms of concentration. All right. So if something is at equilibrium and the equilibrium constant is large, it's larger than 1, that really tells us that the concentration of the product is much higher than the concentration of the reactant, right? Again, if the equilibrium constant, if you're increasing the numerator, the concentration of the numerator is larger than the concentration of the denominator, then you're going to get a value that's larger than 1. So if the equilibrium constant is much larger than 1, that tells you that the concentration of the reactant is much higher than the concentration of the products is much higher than the concentration of the reactant. So when the equilibrium constant is larger than 1, there are more product molecules at equilibrium, right? So we say that equilibrium favors the formation of the products, right? It's still at equilibrium, but the constant tells us if that equilibrium favors the product or favors the reactant. It tells us if we have higher concentration of product at equilibrium, or if we have higher concentration of reactants at equilibrium, right? Well, the opposite is true as well. If the equilibrium constant is smaller than 1, that tells us that the reaction at equilibrium has higher concentration of reactants compared to products. So that equilibrium favors the reactant. It's still at equilibrium. It's still at equilibrium. The rate of change of concentration over time is constant. All right, it's not changing, but it favors the reactant. Okay, well, can we look at the equilibrium constant in terms of the forward and the reverse direction? We can. All right, so again, we're going to use A reacting with B to form C and D. The equilibrium constant is the concentration of the product over the reactant, each raised to its coefficient. But that's the equilibrium constant for the forward direction, right? We are thinking of it in terms of the forward direction, products over reactants, right? If we are writing the equilibrium constant for the reverse direction, right, it's gonna be, if we're looking at it in terms of the reverse direction, then now those are the products, right? They're basically the reactants. And then those are basically our reactants, right? So we swap it. And that's if we're thinking about it in terms of the reverse direction, if we're looking at it the other way around. Or you could think of it that the equilibrium constant of the reverse direction is 1 over the equilibrium constant of the forward direction, right? Again, the reverse is just simply if we're really swapping it, if we're thinking of C and D as being our reactant and they are being converted into A and B, okay, then it's product over reactant, right? So the original reactants are really now the product if we're thinking about it in the reverse direction, right? What about if we have gases? Well, if we think about the concentration of a given gas, it relates to the partial pressure of that given gas. So anytime we're expressing the equilibrium constant for gas, we can also express it in terms of its partial pressure, right? So if we have a reaction and we're dealing with gases, again, C is concentration, well, we can express the equilibrium constant also in terms of partial pressure. So it's the partial pressure of C raised to its coefficient times the partial pressure of D raised to its coefficient, okay, over the partial pressure of each reactant raised to its coefficient. Well, can we correlate the equilibrium constant in terms of partial pressure to the equilibrium constant in terms of concentration? Yes, it's equal to the equilibrium constant in terms of concentration times RT raised to the change in the number of moles. Remember, M is the number of moles, right? And we are simply taking the change in the number of moles of reactant and the number of moles of the product. So it's the number of moles. So delta N is the number of moles of the product minus the total number of moles of reactants. Okay, so when are they equal? When is the equilibrium constant in terms of concentration and in terms of partial pressure is equivalent? When the number of moles don't change, then both the equilibrium constant is the same, because if the change in the number of moles is 0, then all of this is basically equal to 1, right? And again, we're just looking at the change in the total number of moles of the product minus the total number of moles of the reactants. All right, what if we have an equilibrium where we have different phases, gases, liquids, aqueous solution, or maybe even pure solids? Well, anytime we have a reaction that has pure solids and pure solids and liquids, their concentration over in a given reaction doesn't really change. Okay, so anytime we're looking at that equilibrium constant and we have pure liquids or pure solids in a given chemical equilibrium, we do not include those concentrations when we calculate that equilibrium constant. And that's again because the concentration of pure solids and liquids will remain constant, right? It will not affect equilibrium because it will not change, right? So then because B in this case is a reactant that is a pure liquid based on L, its phase, okay, then when we write that equilibrium constant, we simply ignore it. It could be a solid as a pure solid as a product or as a reactant. It could be a pure liquid as a solid or a reactant. Okay, we simply ignore it. So then the equilibrium constant is product over reactant. Just ignore pure solids and liquids. Independent of the concentration of pure solids and liquids because their concentration doesn't really change. So can we calculate the equilibrium constant? Okay, well, let's take a look. If we have hydrogen, if gas reacting with iodine gas to form 2 moles of hydrogen iodide, again, it's the concentration of the product, raised to its coefficient over the concentration of the reactant raised to its coefficient, and we just have 1 mole of each, right? And we are multiplying here, right? So suppose you're told, consider the following balanced chemical reaction where you're given the concentration of each reactant, right? And it just happens to be the same, and you are given the concentration of the product. And you're asked to calculate that equilibrium constant. Again, simply the concentration of the product raised to its coefficient over the concentration of each reactant as well raised to its coefficient, and we ignore pure solids and pure liquids, right? So we get 50, right? If the equilibrium constant is larger than 1, which direction does equilibrium favor, right? That equilibrium constant is large, right? Larger than 1. So it tells us that when the reaction is at equilibrium, it actually favors the forward direction, right? At equilibrium, the concentration of the product is higher than the concentration of the reactant, but we are considering the number of moles because it's raised to its coefficient. Okay, here's another one. It says, given the equilibrium concentrations, determine the equilibrium constant, right? So it already gave us the concentrations at equilibrium. Anytime we're determining the equilibrium constant, we need to use the concentrations at equilibrium when the reaction has reached equilibrium, not the initial concentrations. Okay, so what's the equilibrium constant equal to? Well, we don't have any pure solids or liquids, so we're just going to use the product. We have ammonia and we have 2 moles of ammonia. So we're going to raise it to 2 over the concentration of the reactant. We have 1 mole of nitrogen gas reacting with 3 moles of hydrogen gas. So that's where that 3 comes from. Okay. And for nitrogen, it's simply 1. So we're really not including anything. And then from there, what you would do is you would actually plug in the values. So you have 0.47 molar, and for the reactant, you have 1.5 molar of nitrogen gas and 1.1 molar of hydrogen gas. Okay. Again, just make sure the units are the same, right? Okay. All right. So, oopsie, don't know what's happening here. Okay, so now let's take a look at what if we're looking at concentrations other than equilibrium? Because when we're determining the equilibrium constant, we need the concentrations at equilibrium. Well, what if we don't have the concentrations at equilibrium? Then if we're dealing with concentrations other than equilibrium, then we can determine what we refer to as the reaction quotient, right? And it's the concentrations of a reactant, the reactants and product at any time point other than equilibrium, right? But what we'll notice is for any given reaction, the reaction will always proceed towards equilibrium. So if all we have is reactant, the reaction will tend to proceed in the forward direction so that, it reaches equilibrium. And if the concentration of the product becomes so high, the reaction will start shifting to the reverse direction again, so that it can reach equilibrium. So the reaction quotient, we could calculate it similarly to how we calculate the equilibrium constant, where it's the concentration of the product over the concentration of the reactant, each raised to its coefficient. Right? Notice that we calculate the reaction quotient and the equilibrium constant in a very similar way. It's the same equation. The difference is that anytime we're calculating the equilibrium constant, there's only one value for it. It has to be that those are the concentrations at equilibrium, right? It's always going to be at equilibrium, whereas for calculating the reaction quotient, it's really going to have many different values, right? Initially, and as the concentration, as the reaction kind of progresses, more products are being formed, but it's not yet at equilibrium. So it's really any conditions, and it'll have many different values for the concentrations of the reactants and products at any given time of that particular reaction other than equilibrium. So what do we mean? So let's think of this as, the progress of the reaction that is taking place, okay? Initially, all we have is the reactants. So that's not at equilibrium, that's initially. So we'll calculate it based on the reaction quotient, right? And it's the concentration of the products over the concentration of the reactant. Well, if initially we don't have any products initially, all we'll have is reactants, right? So there's initially no products. So then 0 over whatever value is going to give us 0. So initially, the reaction quotient is going to be equal to 0. Now, as the reaction of the concentration of the product began to increase, the reaction quotient is also going to increase. So that's when this is basically reaching, it's going to pass by equilibrium, and it's going to reach a certain point where Q is, or the reaction quotient is basically equal to infinity. Think of it as the time point when all of the reactant is being converted into product. All right, that's when Q is basically going to approach infinity. Well, at some point in between, the reaction will reach equilibrium, right? And when it reaches equilibrium, we can calculate the equilibrium constant, which is at that point, the equilibrium constant is equal to the reaction quotient. Or you could think of it that the reaction quotient is equal to the equilibrium constant when that particular reaction is at equilibrium. Okay. Why this time point? Equilibrium could have been reached at this time point or this time point, right? So this is just kind of a random spot on here, okay? But think of it as progress, and at some point it's going to reach equilibrium, all right? So what about early on? Well, early on here, Q is smaller than the equilibrium constant. So the reaction is proceeding towards equilibrium. Reaction will be proceeding in the forward direction towards equilibrium. Once it passes equilibrium, what's happening is that now Q is much larger than K. So for the reaction to reach equilibrium again, it's gonna move in the reverse direction, right? So the reaction quotient will basically approach equilibrium and it's gonna shift. It's either gonna shift forward or reverse so that it reaches equilibrium. And that's basically shifting forward direction. When Q is smaller than K, that's it shifting in the reverse direction when Q is larger than K, right? So it's gonna shift so that it can proceed towards equilibrium. So it's going to shift to the right. It's going to shift in the forward direction when Q is smaller than K, right? When Q is smaller than K, it would want to reach equilibrium, right? So it's going to shift into the right, to the forward direction. What's going to happen to the concentrations of the reactants? They're going to decrease, right? And the concentration of the product is going to increase. How do I know that? Think of it in terms of what the reaction quotient equal. It's equal to the concentration of the product over the concentration of the reactant. And as it approaches equilibrium, more product is formed if initially Q is smaller than K, right? So then Q becomes larger until it's equal to the equilibrium constant. And the opposite is true. If Q is much larger than K, then the reaction is going to shift in the reverse direction, all right? And that will increase the concentration of the reactant, decrease the concentration of the product, so that Q becomes smaller, or so that Q is now closer to K, right? So that's the shift towards equilibrium, either in the forward direction or in the reverse direction. Okay, so what causes that, or why? That's basically according to the Chatelier's principle, that when we have a chemical system or a reaction at equilibrium, and that equilibrium is disrupted, whether it's because we added more reactant or we removed some of the product that forms, that equilibrium is going, the reaction is going to shift, all right? So that the reaction will shift so that it will re-establish equilibrium. And by shift, we mean it's either going to proceed at a higher rate towards the forward direction or at a higher rate towards the reverse direction. The idea is so that it can re-establish equilibrium, right? So what happens if we add more reactants, right? If we have reactant and we have a reaction that's already at equilibrium that is forming products, right? What happens if we increase the concentration of the reactant? We just disrupted this equilibrium. So what's going to happen is that the reaction will shift to the right in the forward direction so that more product can be formed. What happens if we add products? Then the reaction is going to shift towards the reactant side, so that more reactants are present. So it's going to shift in the reverse direction or to the left. Remember, pure solids and pure liquids do not affect the equilibrium constant. So there's going to be no change in the direction of the reaction because they do not affect the equilibrium constant. Okay, so now let's consider the following reaction, right? What happens when we add reactants, all right, or products? We have dihydrogen sulfide reacting with oxygen gas, or 2 moles of dihydrogen sulfide reacting with 3 moles of oxygen gas to form 2 moles of water vapor and 2 moles of sulfur dioxide, right? Notice we don't have any pure solids or liquids, so the equilibrium constant is going to be affected by changes in the concentration of any of the following reactants or products. Now, what happens if we go in and we add more of a reactant, right? And we're adding it to a reaction that is already at equilibrium, right? So we're going to see how it's going to basically disturb that equilibrium. So if we add more reactant, then the reaction will tend to want to proceed in the forward direction to form more product. So it's going to shift to the right. What happens if we add more of oxygen gas? Well, oxygen gas is also a reactant, right? So it will tend to want to shift in the direction opposite of the added change. That's one way to think about it, okay? So it's also going to shift to the right, right? To re-establish equilibrium, right? So the reaction is always going to shift to the direction opposite of the added change. So if you add more reactants, equilibrium will shift to form a more product, right? So what happens if we add product to the reaction, right? Then equilibrium again will shift in the direction opposite of the added change. It will shift to the left to form a more reactant, right? Again, it's just a shift, right? And the reason that it shifts so that it can re-establish equilibrium. Okay, well, what happens if we actually remove some of the products? What will happen if you remove some of the products? Which way would you expect equilibrium to shift if instead of adding something, you're removing something? Correct. Equilibrium will tend to shift to the right to form more product, right? So it's always going to move in the direction opposing the change. So if you remove product, equilibrium will shift to form more product, right? So that it can re-establish equilibrium. Okay, so now what if we have a chemical reaction and we know only the initial concentrations? Perhaps we know one of the concentrations of the either reactants or products at equilibrium, or perhaps we only know the initial concentrations, but we also know what the equilibrium constant for that particular reaction is. Okay, remember, it's an equilibrium constant, so it's a constant for a given reaction. Okay, well, we can determine the concentrations at equilibrium by looking at the change of the initial concentration over the progress of the reaction. Well, if initially we only have the reactants, over time, those reactants are reacting to form the product. Well, what's happening to the concentration of the reactants? They're going to decrease by a given magnitude, right? And the concentration of the product is going to increase. So we're looking at that change, what that change might be from the initial concentration to equilibrium. So suppose you're told that you have 0.5 molar of each reactant, and initially you don't have any product. The concentration of the product is 0. When the reaction reaches equilibrium, we don't know the concentrations of one of the reactants in the product, but we know the concentration of only one of the reactants at equilibrium. Notice it's important to now, when it says concentration, is it referring to initial concentration or is it referring to concentration at equilibrium? Well, we're going to solve those by creating what we call an ICE table. Initial, change, equilibrium, ICE, right? So we basically solve it by just simply kind of setting it up as an ICE table: initial, change, and equilibrium. Okay, so this is the initial concentration. This is the concentration at equilibrium. Okay, we only know one of the concentrations at equilibrium, but to determine the equilibrium constant, we would need the concentration of the product at equilibrium, and we would need the concentration of each reactant at equilibrium as well. We can't use the initial concentration. We need the concentration at equilibrium, right? If we're calculating Q, yes, we can, but if we're calculating K, we need them at equilibrium. Okay, so suppose we don't know the concentrations of any at equilibrium. We only know the initial concentration. So an ice table is basically initial, right? The initial concentration, there's no product, but we know the concentration of the reactants that we added. And at equilibrium is what we are going to try to figure out. What is the concentration at equilibrium? Well, we need to determine the change. If the concentration of the reactant is going to decrease by a certain amount, the concentration of the product is going to increase by that same amount, okay? So we do initial, really plus change gives us the concentration at equilibrium. So if the concentration of hydrogen gas changes by X, right? And the concentration of iodide gas changes by X as well. Remember, the reactants, their concentration is decreasing. So we'll label it as a negative X, right? Because the concentration of the reactant is decreasing over time. And that's why we have the negative, right? So the change, it's decreasing over time, right? So then at equilibrium, it's going to be 0.5 minus X. Right? And for the other reactant, it's also going to be 0.5 minus X. What about the product? Would its concentration increase or decrease over time? It's going to increase, right? It's going to increase by X as well. The reason we have 2X is because we have 2 moles of product, and that's where this 2 comes in play. So then the concentration of the product at equilibrium for this particular reaction would be its initial concentration, which is basically 0, plus 2X, right? Notice initial plus change gives us equilibrium, but the concentration of the reactant is decreasing, right? Whereas the concentration of the product is increasing until the reaction reaches equilibrium. So now let's go back to the one where we actually know the concentration of one of the reactants at equilibrium. So we have initial, we have equilibrium, and we look at change. So if you know we're going to just assign it X, that the initial concentration is going to decrease by X. But because we know the concentration of hydrogen gas at equilibrium, we can actually calculate X, right? Because we'll have 0.50 minus X is equal to 0.11. So we basically can solve for it, which is what I'm showing you here. It's like we know that it's going to be 0.5 minus X, but we're given the value, we're told it's 0.11. So it's like 0.5 minus 0.11 is equal to X. So then X is 0.39. Okay, so then the concentration of the other reactant is also going to decrease by X. The concentration of the product is going to increase by 2X. Right, and don't forget the negatives right here. Right, and that's how we would get that. Well, what does it relate to? If we know the concentration at equilibrium, we can now determine the equilibrium constant, right? It's equal to the concentration of the products, each raised to its coefficient, over the concentration of the reactant, each raised to its coefficient, right? So the concentration of the product is 0.78, and we have 2 moles. That's where the 2 comes in play. And then over the concentration of each reactant raised to its coefficients, and it's just 1. Okay, so there could be different variables. You could be looking for the change, you could be looking for the concentration at equilibrium, you could be looking to determine the equilibrium constant. So we'll end up doing problems looking at different variables. All right, I hope you found this one helpful.